So we can start now.
Yeah, yeah, sure. Okay, so guys, yeah. Sir, someone has a doubt. Can we take it?
Yes.
So you can
Hi,
go
sir.
go to the chat in the bottom right corner. Yeah, yeah. He's saying I'm having doubts in week two. Can I ask now? Yeah, sure. You can. I think you can ask.
Hi, sir. Am I audible?
Hello.
Hi, sir. I'm having some doubt in Rutherford back scattering experiment. You showed me some graph, right, regarding the counts, like A, B, C, like that. You showed me some graph in your PPT. Can you please explain that graph? I can't understand what it is.
Lecture number.
Uh, week two. Wait a minute, sir. I will refer it then.
So can we postpone it by a few more minutes and then because I have set up something and I can start whatever I wanted to tell.
Sure, sir. I will just put it in the
At the
chat
end,
box.
you just note down. At the end, we will
Yeah,
clarify that
yeah.
because by that
Maybe
time I'll.
maybe people can put their question in the chat and we'll take them one by one later. Would that be
Yeah,
fine?
yeah.
Yeah.
Yes,
So
sir.
in last lecture, somebody was asking about applications. And in fact, in that discussion forum also, many people have asked about applications. So this slide shows the various applications of accelerators. And as I mentioned last time, that accelerators have become part of our life and they are used everywhere now.
Sir,
Some
sorry,
of the
sir, sorry to interrupt. Can you go to full screen? Maybe that will be good in the slide. So, yeah, yeah. Now it's perfect. Okay.
some of the applications where accelerators are very extensively used, they are shown here. Is there any way to get the pointer here? Show the presenter
Your
view
pointer
and
is coming, sir. You can point.
is
Your pointer is oh yeah, there is a laser
yeah,
pointer.
yeah,
Yeah.
it has come.
Mhm.
So first one which I talked about was national security, and now accelerators are very extensively used for national security. Then accelerator driven systems (ADS), that is for nuclear power production. Then for elemental analysis using various nuclear techniques like RBS, Rutherford backscattering, NRA, EMS means accelerator mass spectrometry, and so on, and PIXI. PIXI is very commonly used for very long time. That is particle induced X-ray emission. That technique is used for elemental analysis for very long time. Earlier, it was used without accelerators. X-rays were directly used. X-rays coming out of radioactive sources. But now accelerators are used for that purpose. Then, of course, material modifications. Radioisotopes protection is the main thing now of accelerators. Earlier, radioisotopes were produced using reactors. But now throughout the world, these isotopes are produced using accelerators for medical purposes, both diagnostics as well as treatment. And they are very extensively used. In fact, now as the reactors are being shut down in many countries, they are looking towards accelerators for production of radioisotopes, which are used particularly very extensively for cancer therapy and diagnostics and so many things. Then, of course, industry thin layer activation, they are used for testing the various elements. For example, in last lecture or last session, I told that many things which go in the satellites to outer space, because outer space there is a lot of radiation. So to see the radiation effect, those, for example, particularly the solar cells, what will be the effect of radiation? Because in outer space, protons, heavy ions, and mainly electrons are there. So to see the effect of those things on the solar cells, because if the solar cell stops working, your satellite launching will be completely failed. And therefore, they should be tested in the lab with the accelerators now, and see that what is the effect of that radiation on those devices. So they are very extensively used for that. Any new element which is used in satellites is first tested in the accelerator lab for radiation damage, particularly, and then only the devices are made out of it after seeing that. Then biosciences therapy. So therapy, I have already mentioned that accelerators are very extensively used for that purpose. Now here there was a small mistake which I think you should use, that this portion is insulator, because if this whole plate is material matter, then there will and this outside one is grounded, and therefore this plate is only from this place to this place, covering only the high voltage terminal. So here this is not there, this part, and similarly on this part is not there. Now, as I mentioned earlier in that lecture, you must have seen in the video that there are three methods to measure the voltage. Now, this is a very high voltage on the terminal. This is called high voltage terminal, and some in some cases the voltage is as much as 15 to 16 or even 20 million volts. So you cannot directly measure it. So there are indirect measurements. One of the simplest measurement is that you have a series of resistances, and then the current will pass through it. There is a meter here at the ground, just before the ground, and you measure the current. Now you are measuring the current, and you want to know the voltage. Therefore, you should know what is the relation between the voltage and the current, and that is what is called calibration. Now, this calibration means that you have different voltages and different current. So you set up a equation or the relationship between the voltage and the current. So by measuring the current, you will know the what is the voltage on that, whether it is 5 million volts or 10 or 15 or 20 or what. So that is what is called calibration. Now, in this calibration, simple calibration, when you are using a series of resistance or resistance chain, you have voltage is equal to IR. IR is the current. R is supposed to be constant, which is the sum of all these resistances. Now, if the when higher current passes through, these the resistances they get hot, and their values also changes. So it may not always be here. It looks like as if it is V is equal to IR is a linear. This linear relationship holds good only if R is constant. So it's a R is a constant of proportionality. You can say V is proportional to I, so that is why V is equal to IR. Now this R is constant. This is a total of them, and you put a meter here where you measure the current. So this was some, but in this case, what was happening? This resistance was not keeping constant. Therefore, this relationship was not really uh, valid, and therefore another method which was used very extensively in the beginning was a generating voltmeter, and that is what I have given in the greater detail. And generating voltmeter, what you do is you have a system GVM, you can see here, where the that instrument faces towards the high voltage terminal, and there is a voltage developed. on the plate which is seen here this P3 we call it, and that there is a resistance across which a voltage will be developed, that and this voltage will be, in this case, will be sort of AC voltage which is rectified, and then there is a meter here. And so again we measure the current or a small voltage, and then that is proportional to the voltage. So the current may be in microampere, but the voltage may be in several milliamperes, this several million volts. So that is what is done. These videos we are having, so I'm not showing in detail. Now this is here that in that one there is a stator and there is a rotor, and one moves and other one is fixed. Stator is fixed. You can see here this is fixed here, this is fixed, stator is fixed, and rotor is moving, which is having slots. So whenever the slots are open, there will be a voltage or the charge induced, or the electric field will be induced in this fixed plate, and that is rectified, and there is a processing done, and you measure the current as is shown here through the resistance and all that, and ultimately you measure a small voltage or a small current which is proportional to the high voltage, millions of volts, on this plate, which is a source. So this proportionality has to be established, because you are not going to calibrate every day. You are not going to see the proportionality constant every day. So once you have to do. Now what happens? The error of this thing comes because the this is not a linear thing. At a small voltage, maybe up to 1 million volt, it is linear. The voltage is proportional to current, or current is proportional to V. But when you go to tens of million volts, then this becomes a non-linear function, and therefore it is absolutely necessary that you do this calibration, or you set up this relation relatively at all the voltages. Now, all the 10 million volts you cannot set up. So what you do is normally that is done by calibration is done by the doing the nuclear reaction, by particularly by resonances. There was a video on that also. You must have seen it, and therefore it is absolutely necessary that you have the calibration done. Some details are shown here. Here, if I assume that the voltage is constant, because it is a DC voltage and it is supposed to be constant, you only want to see the slight variation. That is why the energy experiments are done, to see that how much is the variation. And if you see that, then that current which you are measuring is equal to dq by dt, that is the whatever charge is per unit time is deposited there, and that is equal to v into dc by dt. That c is here the capacitance value. So if your geometry, C will depend on the geometry. So geometry also plays into the role, and therefore before starting the measurements of voltage, you should know how the capacitance value is varying with the voltage, and what is the function of capacitance on the geometry also. So if you do that, then if you do all this mathematics, then C varies as a sinusoidal, because the rotor and the stator are moving with respect to each other. If you do this mathematics, then ultimately it comes that V is proportional to the IRMF. That means that whatever current you are measuring, so, and the voltage developed on the high voltage terminal is proportional to that. And of course, it will not be linear, because when you go higher and higher voltage, many other phenomena take place. For example, sparking will happen, coronal discharge will take place, and all sort of things will happen. And therefore, the calibration has to be done. And calibration means setting up a relationship between the voltage and the current which you are measuring. So the calibration first has to be done with the known sources where you know accurately the voltages, and of course which will depend on the geometry of the voltage source. So whether the high voltage terminal is a cylindrical, or it is a cubical, or it is something else, or it is a so it will depend. So you have to do this, and that calibration is done by nuclear reactions, because nuclear reactions are very accurate. So this is given in the voltage. This is given in one of the videos, very explicitly mentioned, and so this was that is why the calibration is absolutely necessary. Accurate calibration is required. So calibration is nothing but setting up a relationship between the parameter which you are measuring and what you have measured. So relationship between them. Here, for example, you want to measure the voltage, which could be very high, and and you are measuring a current which is very small, because you are measuring across a very small. See, for example, in the first one where said that you have a series of resistances, large resistance, let's say 100 resistances are using, and all the resistances have to be equal, and suppose some resistance value changes, then that will affect your calibration, because that will affect the resistance value, and hence the current which is passing through that which you are measuring. And therefore calibration is absolutely necessary if you want to know the accurate value of voltage, and hence the energy of the particle which you are using for the experiment. Because ultimately your aim is to measure the energy, and use the energy for nuclear reactions, and for that you should know the voltage, or you should directly uh, know the energy. So this was the clarification for that question which Arup Krishna asked, that what is the meaning of calibration. So calibration means is setting up a relationship, and if it is done point by point at low voltages as well as high voltage, middle voltage, everywhere, then the measurements will be more accurate. Second question which everybody has asked is that what are the applications of accelerators? This many people have asked, so I thought that I spend some time on this. I will be showing several slides on this. Uh, Although you will be seeing these slides again in different lectures, but this will be a repeat, and I think it will be good to, if you know a priori before attending the videos. Now, as I mentioned that accelerators are now integral part of our life. I think everywhere accelerators are used, whether they have become like a household items. If you remember it, that earlier we were having the TV, which was having vacuum tubes, and there one accelerator is used. In fact, all the components which are used in the accelerator, they are all there, and that is perhaps one of the best most accurate because if your that accelerator is not working properly, the image will not come out to be properly. So so you when you start the morning with a cup of tea, you see the first accelerator. Of course now the TVs are smart TVs, and they are having different kind of arrangements, but earlier TVs were having these accelerators where all components which are used in the accelerators were there, whether they were lenses, where they were magnets, or they were electron source, or anything which was there. But now, those were the accelerators which were low energy accelerators. For example, now in color TV, we use about 25 kilovolt accelerator. Now the accelerators with the central mass energies of 14 TeV and even more are available. And therefore their magnitudes and the technologies, everything has changed. So I will just show you a few slides which will give you some idea that what are the applications. For example, if you see the application, all accelerators were developed for discovery science. Discovery science basically is a basic research. And one of the thing which all the scientists, particularly the physicists, would like to know the what is the origin of the universe. and how it has evolved. Then what are the fundamental particles which form the building blocks for everything? Protons, neutrons, and so many now are there. So we would like to know how many particles are there, what are their sizes, how they behave, what are the forces between them which is holding them, and then what are the types of forces which are existing. So unification of forces has been a very hot topic now. So that you will like to study with using the accelerators. Then one of the very interesting thing is production of super heavy elements. See, for example, as of now, we know only up to uranium, plutonium, and few things. Now, if you see the beta stability line, then you see that naturally occurring elements are up to, let's say, Z is equal to 92 or 95 in that region. Mass is up to 250 or something like. Are there heavier particles which are available, which can be formed? Those are called super heavy nuclei. In where the Z or the atomic number is of the order of more than 100, and masses could be around 300 or more than. Now if you are able to make them and use them, then many things will become very simple. Then you will have that, if suppose you can have a reactor based on the mass is equal to 300 or 350 elements, that kind of atoms or materials, then you can make a reactor which is pocket reactor in your, because the number of neutrons which will be available will be very large, and therefore they are very useful. In addition to that, of course, for basic research they are very important. You would like to know what are the properties of those super heavy elements, whether the physics, your conventional physics which you are using, that is usable in those things or not. So you like to study. So up to now, the elements up to about Z is equal to 118 have been produced in lab. 120 also has been produced, but the only few atoms, and the properties of that could not be studied when, because there are only few atoms, and but up to 118 they have been thoroughly studied and they have been named also. 120 has not been named yet, and I will show one slide on that. Then, of course, today the accelerators are very useful to the society. They are used for security, national security, particularly food irradiation, preservation, then medical purposes, and then environment. And of course, the latest application of accelerators is production of nuclear energy, and that is what is called ADS. So you will see that there is a lecture on the one video is there on this ADS, accelerator driven system. So I'm not going much details. So just give you some example, because the I have not given the references, and IPR may be involved in it. So I just show you that this I have taken from the Google, that because of accelerators and good detectors, we have been able to now study the protons, neutrons, and all particles. What are their constituents? What are they made up of? For example, if you take a proton, then this is consist of so all baryons are made up of three quarks. See, for example, proton is UUD, up quark, and this is down quark. And in one of the videos, I have shown their properties. So I'm not talking about here. So you can see that there are six quarks: up, down, charm, strange, top, and bottom. And similarly, there are six leptons here shown. So these are all things have been studied, and these are the carriers. These are carriers of these forces, which are, and recently this Higgs boson has been studied at CERN. So these all has been possible because of accelerators. Few years back, a discovery, I think is a very discovery. So far, the all the physics was telling that all these nucleons and these particles are made up of only three quarks. For example, proton is up UUD, neutron is DD, neutron is UDD, But recently, five quark systems have been detected, and this is sort of you can call it is a discovery, and this needs a fresh, different kind of physics to be models have to be involved, and everything has to be relooked. Now, I have sent today morning. As a attachment one lecture by Cody Folden from Texas AMU University, and he has given a talk on exotic beams in one summer school, so you must have received it, which talks about what are the super heavy elements and what are the experiments. And it's a very nice paper, a very nice talk, and I think all of you should go through it. So as I mentioned that Z is equal to 118, which has been named at OG after the Russian scientist who discovered it in Dubna accelerator in Russia, and Z is equal to 120. Few atoms have been produced and studied. In fact, in the beginning, only one atom was produced. Produced meaning there may be more, but by putting all the constraints, one was definitely identified as Z is equal to 120. And unless you produce large number of atoms, this will not be accepted and studied. You can see how these super heavy elements have been produced and what are their names. They have been named. For example, 118 has been named after Russian scientist, which you can see here. So different elements have been produced at various. So four labs which are mainly involved in this exercise is Dubna in Russia and GSI in Germany and RICAN and other KEK in the Japan, and many, and CERN of course is also involved in it. Now these are accelerators which you will see later on. CERN is a accelerator where the two colliding rings or two colliding beams are interacting with each other. Each one of them is having energy of 7 TeV each. So the center, because they are coming from the opposite side, so center of mass energy will be added. So its center of mass energy becomes 14 TeV. And this is one where recently the Higgs bosons have been discovered. So this is a one, and the other one is a Tevatron at Fermi Lab in Chicago. There, 1 TeV beam. This is a very old machine and is still working. 1 TeV proton beam interacts with the 1 TeV anti-proton beam. So this is different from Sun. Sun, both the beams are proton beams. Here is one beam is proton beam, other one is the anti-proton beam. So you can study the physics of particle anti-particle collisions. So this is also very important one. The third one, which is coming up, I think it has started working, is a fair in Germany, in GSI, and there it is called Facility for Anti-Proton and Ion Research. So ion and anti-proton, and this will be the biggest accelerator in the world at this moment, at any stage. So it consists of several rings at the and injector is proton linear. Then three rings are there here. You can see the last ring is uh, with the b rho is equal to 300, and it can accel. The advantage of this accelerator would be that it can accelerate all the particles right from proton to uridium. So for uranium, for example, the beam energy will be very, very high, several hundred TeVs, but it has to be then divided by 235 or 238 to calculate the energy per nucleon. And that is what matters in the nuclear reactions. So this is a very good machine. Another accelerator will be coming, which has been now approved now, is a ILC International Linear Collider, which will be a electron positron collider. So these are LINX, So one from one lineage it will be a electron beam, from other side the positron beam, and they will collide. And this, so in the second, this is being made in the, now the location is decided that it will be Japan. Earlier, India was also one of the contender. It was thought either it will be in USA or maybe Europe or India. India means Asia, either Japan or the India. But ultimately, it has been decided that it will be in Japan, and it will be made in two phases. First phase, the length will be about 31 kilometers, and in the second phase, which will accelerate the beams to about 500 GeV each. So the total beam will be about 1 TeV total energy, and the length will be about 51 kilometers in phase 2 when it is completed. And the linear accelerators, the whole system has to be aligned within the some millimeter errors are possible. So you can see if a 51-kilometer long linear accelerator, each component has to be aligned with the respect to each other within microns, hundreds of microns. So it's a difficult task, but then the this will be able to we will be able to use this electron and positron collider because they are fundamental particles. So the energy will be fully available. It will not be per nucleon. It will be fully available, and the signals, because they are fundamental particles, so they will be signals will be very very clean. So you will be able to do much better discoveries as compared to protons and neutrons. See, proton, if you take, if a proton is colliding with the other proton, then it becomes three quarks versus three quarks. So it becomes a six quark system, six particle system. So the other errors also get into it. So the signals are not very clean as compared to these electrons and positron accelerators. So these are some of the, just to inform you about it. Other one is the applications in the healthcare. For example, this is a old report in 2008. Almost like 25,000 accelerators were available, and 27,500 were available in 2008. This is a report which has compiled the accelerators throughout the world. And these are various applications you can see. And you can see here that the facilities available earlier for basic research were very few. Now, of course, and that is because the facilities which have to be used in basic research are very big, very costly, huge ones. Even to operate them is very difficult. And there are only about 250 facilities for research purposes. But each facility, if you see the cost of these 250s is more than the 27,000 of them. Of course, now there are a number of accelerators are increasing, and it is in 2015 it was compiled. Compilation said that there are about 40,000 accelerators, and now of course they have crossed more than they have crossed 50,000. One of the biggest application is a cancer application here. As I said, I have already. So two, three kinds of machines are used. Earlier, you remember that we were using X-rays or gamma rays. Then it went to the proton therapy. Why we have gone to proton therapy and neutron therapy, and now it is ion therapy based on the heavy ions like carbon or even heavier ones. Why it is important to use them is shown here. For example, they are all, as I said in the beginning, that they are not only used for uh, uh, treatment, but they are also used for diagnostics purpose. And fluorine 18, which is a positron emitter, is very extensively used to detect the cancer, and there are many others. So at low energies, we can, through the nuclear reactions, we can produce fluorine. But if you want to produce these other isotopes, which are used for the diagnostics as well as treatment, then you have to go to higher energy accelerators. Here it is. So what you do is that you bombard a beam of bombard of proton on a oxygen 18, then fluorine 18 plus is produced here, and plus neutron will be there, I think. And the Q value of that will be something. So it will have some energy. And there are two ways of doing the diagnostics. One is PET and other is PETs. I'm not going through that, how a diagnostic is done. So this you can see is radioactive elements are used for diagnostic purpose. So you inject, let's say, fluorine 18 tracer along with tracer, and then it gets collected at the site of this cancer, and with the surrounding electrons, when it combines, it annihilates, then positron and electron, they will emit two gamma rays, and as the due to momentum conservation, they will go in opposite direction. So these are gamma rays which are going, and there is this circular ring which has many large number of detectors. They will detect the gamma rays and they are processed. From that, you can exactly know the location of the cancer as well as their size, etc. So you can do the analysis and you can exactly find out the location and you can do the treatment properly. This is one accelerator. Cyclone is a cyclotron, 16.5 MeV cyclotron. And as I mentioned it, that low energy cyclotron, low energy accelerator, you can produce only light ions through the reactions. And these are the reactions, these are the elements which are produced in this cyclotron. Fluorine 18 is produced most of the time and supplied to several hospitals, Bombay and around. This is another technique where the mainly it is used for brain cancer. It's called BNCT, or it is called boron neutron capture therapy. So neutrons are produced through reaction, and then the boron is injected as a delivery agent. And when these neutrons react with the reaction takes place with the boron, then lithium plus alpha comes out, and so you irradiate the cancer cells with the neutrons, and which are produced through the reaction through the accelerators, and then the cancer is killed. Cancer cells are killed. You can see the effect of that tumor. You can see that there was a tumor here before. This was a tumor, and after the irradiation, it has disappeared here. After 6 weeks of treatment with the beam, this is completely disappeared. It's a brain tumor. Now, this I have already. Now, the I will tell that what is the advantage. See, earlier X-rays therapy was used, and I'll just show. Oh, I'm not able to show. I'll show you at the end. There is a video here, a small video is there, where this only shows that here the X-ray beam, if it is bombarded, this is a tumor. This white thing which you are seeing is a tumor, and when the X-rays produce, it passes through the whole thing. So it will not only kill the it will kill not only the cancerous cells but also kill the healthy cells. While in the case of protons and heavy ions, it just comes here and all the energy is deposited here, and nothing happens to these cells, outside cell, and then that is coming here. You can see that the reason being because of Bragg curve. This is because of nuclear reaction. We call it a Bragg curve here. So you can see here that suppose this is a skill level, so that the depth of the tissues cancerous cell, if suppose it is well inside, let's say 20 centimeter or 20 millimeter or whatever distance, 20 centimeter or inside, Then if you are putting, let's say, X-rays or the electron beams, most of the energy is deposited here only. So you can see that this region, most of the healthy cells are destroyed. While if you have heavier, let's say, proton, the phenomena is such that the energy loss is something like this. So that means almost 80% of the energy is deposited at that point where this. So this where this cancer cells is there, and this peak you can shift by varying this energy. So the advantage of having proton accelerators, for example, in, for cancer therapy is that you do not kill the healthy cells. You kill only these cells by depositing most of the energy at that place. At that place, that location, the depth, you can choose by selecting the energy. And suppose the cancer cell is here, cancer is here, then you can see X-rays or electron beam. The energy left here is very small. Most of the energy is lost in the beginning itself. While proton, in the case of proton, it is you can choose this. So most of the energy will be lost there. While in the case of carbon beam or heavier beam, let's say this is proton, it becomes even sharper. So suppose the cancer size is only few millimeter, then you will not like to have a bigger beam. So this peak sharpness increases further. But there is an advantage in the case of heavy ions that you can smear it, and if suppose the cancer size is bigger, you can really get the bigger area where you can see here this black peak. You can, instead of very sharp, you can make it slightly top. You can make it slightly flat. So you can, if suppose the cancer size is this much, then you can make beam size also that much by, and you can see that you can treat the cancer very well. So that is the advantage of this. So for that earlier, and since these heavy end facilities, they are very expensive. So right now there are only few facilities. For example, GSI is having in Germany proton facility. Japan is having. China is having. And for example, proton, there are a lot of proposals now. This I came to know that few weeks back, this proton facility for cancer therapy has started working, and I think they are still doing the trials on the. So there is a one accelerator here in India, in in Extract in Kharghar, the New Bombay. France is planned, Italy, Sweden, several other countries have planned. So India has also planned. Now this proton facility has started working, and they are going ahead with the carbon based facility, heavy ion cancer therapy. There are many other applications which I will not go through it. One of them is AMS, and you can see these are the isotopes which are used. For example, carbon dating we have read even in 10th class it is taught now. And with there, what you do is that carbon 14 to carbon 12 ratio you measure, and from that you can find out the age of that sample. When suppose some tree died, cut it is cutted 1 million 1 million years ago, then you measure the carbon 14 to carbon 12, and then from the ratio you can find out what is the age when it was cut. When, so when live is there, when anything is live, that time carbon 14 keeps in building up, and whose lifetime is about 5,730 years. And as soon as you that thing is dead, then carbon 14 making goes to zero, and then the ratio will decrease. And from that ratio, you can find out. You can plot, and you can find out. And this has been very extensively used for example, they find the age of the mummy, which is here, which was kept for very long time. And these are, so this is not only the carbon 14 dating, but it is now used. This technique of AMS is used for various other fields, archaeology, astrophysics, environmental science, hydrology, oceanology, geology, and many others to find out what is the age of Himalayas. Also, experiments are being done, and that way it can be. And of course, tandem accelerators, which I have talked about, are called the ultra sensitive mass spectrometer for this, because you inject the negative ions, and the reason being that, for example, you are measuring carbon 14, so the nitrogen 14 which interferes does not form negative ion. That is why it gives a very clean signal. Similarly, argon 36 and xenon 129. For example, one xenon 29 negative ions don't exist, which interferes with the other. Now this because there will be one full video, so I'm not going to talk about them. But this is one. This I wanted to show that we need a system which can use thorium, and you can see this table, which is an international table, that India has highest amount of thorium, good quality thorium. Almost 60% of world thorium, good quality thorium, is in India. So if we can use a thorium in the fuel cycle, then I think our problem of fuel, nuclear fuel, which is at this moment is based on uranium 235, or in fast breeder reactor as a plutonium mixed with the other thing, that will be sold for as I said, almost for 500 to 600 years. So this you can see the amount of thorium, good quality thorium, in different deposits in various countries, and you can see India is on the top. So almost has about 1 million tons of it's about 16% of what thorium is in India. So this was realized long back by DAE, Department of Atomic Energy, and uh, nuclear energy program was developed in the stage wise. And the third stage, which should start now, uh, thorium was is supposed to be used very extensively. And these are the equations. See, thorium itself, as I mentioned, is not a fissile material. So, but when you bombard neutrons on it, ultimately it gets converted into uranium 233 or plutonium 239 in the case of uranium 238, which is 99.3% of the uranium, and which is a big problem actually. This is a radioactive waste, we call it. So at this moment, depositing that into a safer site has become a big problem. So if we can utilize this facility, then I think your problem will be solved, not only of power but also the nuclear waste. This is the diagram which was given by Professor Carlo Rubbia, who is a Nobel laureate, and he said that we can use accelerators for this as an energy amplifier for generating the nuclear power. And after some time it becomes a self-sustaining. You don't need any power from outside. You can see that in this system 240 megawatt is produced here. Out of that, 60 megawatt again goes back to the accelerator and then comes back. So effectively you provide 180 megawatt to the grid, and your accelerator, target gain, everything becomes self-sustaining type. So this will be a very useful tool, and that all happens because 1 GeV neutron, 1 to 1.5 GeV proton beam, when it falls on a heavy target, it produces about 10 to 15, up to 10 to 15, or say for example at 1 GeV, if you take about 1 GeV here, it will produce about 25 neutrons per proton. So you can see that, because ultimately power is produced by neutrons. So if it is a fast neutron, you slow it down and then the fission takes place. So more the neutrons you produce, easier will be the target. More this energy will be produced. So in the case of, for example, 1 GeV proton falling on some heavy target will produce about 25 neutrons, 25 to 30 neutrons in that range. So it is a very good, and you can see that there are various ways to produce neutrons, and this ADS is the best way to. It consumes the minimum amount of energy. Well, for example, DT fusion, it involves about 10,000 MeV per Newton, while this is only 27 MeV per Newton. So this is a very efficient way of doing it. You can see here that what kind of accelerator you need. You can see if you want to produce about 3000 megawatt thermal power, then you need about, if you are using 1K, which is 0.95, then you need about 90 milliampere current. If you use 98, which is now possible, all the studies are showing that this also is safe. So it reduces to about 30 milliamperes. So you need this kind of accelerator for so this was a cartoon given by that these are very you have to really concentrate, and this was a passing thought which said that in a lab, the nice thing about this research lab, particular lab, this is a joke only, is the scientists here are all the time out attending seminars, leaving you completely undisturbed for doing this research. So this was there were some of the applications which which I thought there are a large number of applications, but what I thought that I'll give you some idea about. So you will see. So this was some of the applications which I wanted to say. I wanted to give you. So now you can, I think.
Thank you, sir, for the very nice presentation. Uh, and it was very insightful. I hope everyone will benefit from it. Uh, as so, you want to
This
stop sharing? Just click on the stop sharing button, the blue
this
button you can see. Yeah. Okay.
Okay, okay, thank you. No, I'm
And
not very conversant with this,
yeah, it's no problem.
so
So,
I what I will request all the participants is that I have sent as a attachment
mhm.
one PDF file which describes the history as well as the kind of experiments which have been done to produce super heavy elements by that Texas professor. You please go through it. Is very interesting. I found it very interesting. So you just have a look at it.
Okay, and we have some questions on the chat box. Uh, can you see, sir? Dhanush has asked and Mohit has asked one question.
Now the questions we can ask the questions. I'll answer them.
Yeah, they have asked two questions. Can you see? Dhanush.
Yeah, I can see now that.
Okay.
No, if I can you tell what is that? I have doubt in the week two because I have not opened my
No,
laptop,
no.
so
So
I
he
don't know
has
what.
asked the dot. In the next question, he has asked, just see
Please
below.
go ahead with the good your questions here.
After
We will
that.
take them. Acha, that is yours.
Yeah. After that, he has
In
asked.
week two, so six we so I what I will do is that I will open the lectures now. That
Sir, I think that would not be necessary. It's very, I
if
think.
they ask, then I can if you ask the question, then I will answer it.
They
But
have. He
otherwise,
has
then
asked.
I have.
He has asked. He is asking about the Rutherford back scattering experiment, where there is a
Okay.
graph between counts and a scattering energy. He wants to know experimentally how it's recorded.
No, so if you have the beam is coming falling on a target, let's say proton beam or something, that was connected to the calibration of the energy. Basically, it was a nuclear reaction. So if it is high energy, then nuclear reaction will take place. But if it is low energy, below the Coulomb barrier or about Coulomb barrier, then the atomic reaction will take place. So it will be one of the very famous experiment or the process is Rutherford backscattering, and that happens only below the Coulomb barrier, around the Coulomb barrier or below Coulomb barrier. So these particles they don't make any nuclear reaction, but they is get scattered, and the energy of the scattered particle will be decided by at what angle this particle is coming. So back scattered means this. Suppose this is the target. So and the beam is coming from this side. You can see my. Uh,
Yeah, yeah,
then the detector is mounted on the backward angle. See, it is going from 0 to 180 degree. So if the detector is mounted at 160 degree or 170 degree, then the resolution will be better, and the particle of these scattered particles, as most of the particles will be in the forward angle, but some particles will go to the backward angle also. So there you put, suppose it is a proton, then you want to detect the proton. Let's say proton beam was coming. It is scattered to the 160 degree. In our case, for example, we kept it 160 degree. 160 degree, you put a detector which will detect proton charge particle detect. If it is gamma, then it is different detector. If it is proton, it is different. If it is heavy ion, then it will be different detector. For example, for proton, you put a surface barrier detector. Then you measure. Now, what surface barrier detector will do it? This particle will interact and create a charge, and that charge you process it, and ultimately either it is converted into a current or a voltage, small voltage, which could be millivolt or something. Then you have all the devices which will take care of this. They will rectify all the errors, and or all the, so a very clean signal you will get, and you will get the energy. You have to again calibrate it. See, calibration is a must. So because you are getting only millivolts, energy of the proton is in MeVs, million volts. So and from that you are getting a millivolt signal. So this millivolt signal which you are getting through the surface barrier detector, you are calibrating with respect to that. So that means you know what is the, so first this calibration in any nuclear physics or atomic physics experiment, first the calibration is done with the known sources. So suppose I get 1 millivolt signal, what will be the energy of that particle? If suppose 5 millivolt, then what will it? So calibration curve is there. So once you know the calibration, and you know the what is the signal strength, you can see what is the energy. Now, if you know the energy, then theoretically you can calculate what was the angle. You know the angle, so you can calculate exactly the energy. If you know the exact energy, scattered energy, you know the angle, because that you are measuring at what degrees or what angle you have mounted your detector. That has to be accurately known. Then you can calculate the incident energy. Incident energy to the scattered energy, there is a relation depending upon the kinematics. That formula I have given in the video. So this is how it is done. So you have a beam, proton beam. Let's say proton beam you want to calibrate it. Proton beam. Then there is a target. Target could be any tantalum or any target which is well studied. You have to know the thickness. So that means before mounting the target, you have to measure the its thickness, because there will be some energy loss in that one. And then the beam is coming out of it. At what angle you are measuring, because all particle will go from 0 degree to 180 degree all along. So you have to know at what angle exactly you have put the detector. So this angle you know the what particle you is. So particle mass know the, but you don't know the energy that you want to find out by this calibration. So once you know the energy, this will react with the detector, which is a surface barrier detector, which is used for charged particles. If it is gamma ray, then it will be something else. It will be germanium detector. Gamma ray is different detector. jelly or silly, or there are several. Silly is for this charged particles. Jelly is for this. The germanium detector is for use for that. Or high HPG, high purity germanium. So you know that from that signal will come, which you will process. You know what is the. So first, what we do is that you will put several targets, several sources on that detector, whose energies are known. So with that, you will draw a curve that okay, if I get 1 millivolt, this is the energy. If I got 5, so that calibration is there. Calibration chart is there. So when you get in actual measurement, you get the signal, you know that what is the energy of this. Energy of the particle which has scattered at 160 degree or 150 degree, whatever angle you have set up. Once you know this, then through kinematics you can calculate what was the energy of the incoming particle. That relation is there. That relation E scattered upon E incident is equal to kinematics. There is a formula. So from that you can calculate. So this is how it is calculated. I hope it's clear.
Sir, it's clear, sir, but my doubt is something more. Can I ask it now?
Yeah, yeah, please, please.
So what I was saying is I can understand that we are using a proton beam and make it to strike on a target, and then we are collecting the backscattering beams. That's all fine. But up to a scattering energy, let's say 4.5 millielectron volt, the beam was coming back. The scattered beam are coming. But
Hmm.
after 4.5, all of a sudden, why the counts are going to zero? What happens if you increase that energy, or what happens after that energy?
Okay, because the thickness of the detector is small. So see this to generate the counts, you have to have detector material, isn't it? And detector
Yes, sir.
thickness is only some 25 or 20 micron. And this beam which you are putting, let's say even 5 MeV beam, has a much larger range. So it will just pass through it. So it will fall on the back somewhere where there is no reaction taking place. So there is when there is no reaction, there is no count there. So count is there only in the 20 micron thickness of detector. You understand?
Yes, sir.
Is it clear?
Yes, sir. Yes, sir.
See this detector thickness is only something like 20 to 20 or maximum 50, because there it is very difficult to make those detectors of very large thicknesses. So any detector, suppose it is, let's say, even 50 micron detector, which is very uncommon. Most of the detectors are 20, 25, 30 micron. Now this particle will pass through it, and even very small energy particle will pass through that 20 micron. And after it is on the backing of some heavy material or something, steel or something, I don't know, which are the backing materials used. There, because it is heavy, though, so there is no scattering will take place there. This particle will be absorbed there, and it will generate some current there, the charge is depositing there. No reaction will take place, because the Coulomb energy or the reaction energy will be required is very high. Suppose, see for example, if the target is high Z material, then Coulomb energy also will be high. That means you need that much energy to produce any reaction or any scattering. Rea- so that is why nothing will happen there after this 20 micron thickness detector. No reaction will take place. So no reaction means no count.
Sir, are you saying that the scattering energy is a function of incident energy? So if you keep
Yes,
on
yes, of
increasing,
course, yes.
yeah, if you keep on increasing the incident energy, means the particle will penetrate the target and it will there will be no back scattering, or the particle will get back scattered,
No,
but it
this
can't.
I am not talking right now. I am not talking about the target thickness. I am talking about the detector thickness.
The detector
If you make,
component.
if you now let me take it target thickness. If the target thickness normally in for nuclear reaction or this scattering reaction is very small in micron only. But if you suppose you make a 1 millimeter thick target, then you see that there will not be any back scattering because all the beam will be lost there. You have to see what is the range. Suppose you have 10 MeV beam and its range is only half milliampere, and if your target is 1 milliampere, in half millimeter it will be lost there. It will stop there, so nothing will come out of on the back, isn't it? There will be some scattering on the front from the surface, but nothing will pass through the target. So target is such, and in that case, suppose target is always very thin target because we want beam to pass through. Otherwise, no, if all the beam is getting stopped on the target, then this beam is nothing but the heat. It will generate the heat. The target will get hot. So even the microampere beam will make this target so hot that it will be broken. So target thickness is very small actually. So most of the actually 99% of the beam passes through the target, and very little is no effectively no beam is lost in the target. Only some energy is lost, but the particles are not stopped there. Target thickness has to be very small. So if target thickness is large, then all the beam will be lost, no scattering on the back side. Back is RBS will be zero. So you cannot use this technique at all.
Sir, so you are saying that the target thickness must be so small, then only you will get the backscattering thing, right?
Sure. Now this so small we have to define, because that you have to compromise, because you have to have enough number of atoms also, because it is the interaction of the beam with the atom. It should not be zero, because if it is zero there is no scattering. So you have to have some target thickness which this beam will encounter in such a way that some interaction will take place. See, suppose if the target is so small, then the number of particles scattered also will be very small. So you have to optimize it. And secondly, I will give you this is theoretical. Now I tell you that this whole thing is mounted inside a chamber, which is uh, which is having vacuum. Now, if the target thickness is very small, then when you start pumping it, the target will break within no time, because that the pressure with which this pump will suck the air inside the chamber. And this target, if it is a very thin target, it cannot. But at the same time, you cannot have very thick target for two reasons. That if it is very thick target, see, when the beam is passing through the thick target, it is losing energy. And losing energy means it is not, suppose this is 1 MeV, let's say beam, and it has got 100 kV. It is not there is will be some spread, and that spread is nothing but it will spoil the resolution. It will give uncertainty in the energy. So you would like to, so these are contradictory requirements. You have to have very thin target to get very good resolution, but then if you have very thin target, then the number of atoms reduces, so the count rate comes down, and then the target will break also. So you have to find that how much should be the target, so that all these conditions are met in such a way that you are able to do the experiment.
Okay, sir. But in the graph you showed three graphs, right? 3 counts like A, B, C.
They are different targets.
Oh, okay. So what exactly it signifies at this angle? For let's say 4.5 milli electron volt if the curve gets zero means, or else 5.2 milli electron volt the curve gets into zero means. What exactly it signifies?
No, these are different. As I said that, see, this scattering depends upon not only target thickness but also target material. So suppose all of them are roughly of the same thickness. Let's say I'm just putting it. Then where it will go down, see, it will depend upon what is the mass also. So if we have taken three targets, of different materials. So the peak at which it will start dropping down will depend on the material, and their energy will also, because the energy loss will not depend on the target thickness alone, but also on mass also. So the peak of that peak of the, here in this case other chord, it is flat and then it will start coming down. And the beauty of this is it comes down very sharp. So these three targets are to get the three energies, because we know that this target, the roughly if the thicknesses are same, and you can take into account even if target thicknesses are different, can the calculation, you can take care of that. So if the masses are different but the targets are different, that those things can be taken. But let us suppose, to simplify the issue, that all the targets are same, then depending upon the atomic masses of the target, the energy of that sharp edge where it starts coming down to zero will define, because the energy loss depends upon on the atomic mass also. So it's, so the your calculation about the energy resolution and energy measurements become much more error which you are having in that will become less.
Okay, sir.
So
Thank you.
if you are having, see, it's like this, no, that if you have only 2 points and if you draw the straight line, then the error will be very large. But if you have 10 points and draw the straight line, the error will be much less. So we have used three targets to reduce the error. And we have used the three targets to, which will give the different energies. So that this calibration, this is again a calibration. So the calibration error becomes much smaller.
Okay, sir. Thank you.
Okay, so then we can go to the next question by Mohit.
Mohit,
I think he has left the meeting, but anyway, you can answer the question. And
it is Mohit, na?
yeah, Mohit Ratanpal.
This assignment one, kindly clarify on a question. Dipole magnets can also focus. Yeah, this see, focusing basically, as you have, if you derive the equation, it is the components. See, suppose the beam is going like this, then the velocity will have two components. One is perpendicular to this and one is so the one which is along the beam is giving the energy, but the perpendicular one, that means that force which is responsible for diverging the beam. So if you can somehow reduce that, and by reducing, how you reduce that? By applying the magnetic field which are restricting this. Now normally in the case of hard edge magnets which are like this, you have only component which are the beam is the magnetic field is just perpendicular to that poles. Now if these poles you can shape in such a way that this magnetic field is also having two components, then depending upon now north pole south pole, either the beam can be thrown away or it can be brought back depending upon whether the force is positive or negative. So this is what I am saying, that the dipole not only bends the beam, one component will bend it, the other component, if you drive the force, then either it will throw the beam out or it will bring it depending upon direction of the. So if you edge, that is called wedge. That means your magnet is not just like this, but you cut down the taper down the, so that there are components. Two components are generated. Now, if you have two components generated, that means the force and direction is such that it will bring back the beam. The force direction will change. So dipole beam, in many accelerators, people have used dipole magnets for both bending as well as focusing. Otherwise, you have to use for focusing quadrupoles and some other lenses, which can be partially compensated. But here the problem is that if you taper the wedges, then the region in which the magnetic field is constant, that reduces. So again, you have to optimize it, because you would like to have, see, when you are calculating the force, you use the expression where you use v cross b is constant, you are assuming. Now if you are tapering the magnetic field, this magnet pole, that means the region between the center region is reducing, where it is perpendicular, magnetic field is perpendicular. So then you have to increase the size of the pole. If you increase the size of pole, then the cost of the magnet goes up. And also, then to get that magnetic field, you need much bigger coils. You have to pass on much bigger, much larger currents. Then the cooling becomes a problem, because if you are, so you have to optimize again. So normally in low energy accelerators, it is found low, when I am saying is less than 100 MeV or something like that, is that if you use them separately, it is good, better. Then the operation wise also it becomes much simpler. But if you go to GV, time of accelerators, then it has been found that these dipole magnets, because their dipole moment magnets are equally important, because the beam has to move into the circular path, or whatever, not in the straight line like linear, but sir, then you have to continuously use the magnets, dipole magnets, to bring back to the trajectory. There, it is found that if you keep adding this this field, which brings back continuously, then it is easier to get the beam back to that. So by tapering the beam, and those magnets are called wedge magnets. That means you are tapering the poles on either side of that, so that to generate a component which will bring back the beam, which will give a negative focusing force. That means it will bring back to them. That is there. So if you search in Google, if you search wedge magnets, this you will get. But in one of the videos, I have talked about wedge magnet little bit, very little magnet.
Just I want to add one sentence that in week 9 in lecture 26, these age focusing and effects of the bending magnet due to their ages will be covered.
Correct. Yeah, that's right. Yeah.
Okay, that's great. Okay, anyone else has any question? They can ask.
Have a doubt.
Yeah, please go on.
In carbon therapy, the carbon ion size will be greater than proton. So greater than proton interaction in the tissues. So how it is useful than proton therapy?
No, see, you are comparing proton and carbon therapy. Now, you see, basically, if you just consider it in I'm not talking about physics now. See, basically, carbon is 14 times heavier than the proton. So roughly, if the energy of two proton as well as carbon energy is much larger. Mass is 12 times larger. So the heat generated, basically, if you listen layman's language, I'm not talking about nuclear reaction, this and that. How these cancer cells are killed? By it, they are killed by when this heavy ion or proton goes and departs there, is having a lot of kinetic energy, and it generates heat there basically, and it just burns those effect is like equivalent to that. It burns that. So this, since the energy transfer here, because the mass is much larger, or energy per nucleon is same. So the momentum which or the heat which is generated on that place where it is stopped. See, I am say both of them, proton as well as carbon, both of them have to stop at that place where this cancer is there. So when they are reaching and depositing the energy, and since in the case of carbon, it is a very large amount of beam because of Bragg peak is deposited in a very small region. So most of the energy or the is deposited in a very small region, and therefore the heat generated there will be much larger. It's not nuclear reaction. I indirectly you can call anything, but effectively carbon for carbon 12, the heat generated will be much larger as compared to proton. So these cancerous cells or anything will be deposited. But energy has to be sufficient. So if suppose, for example, in the case of proton, the optimum energy which has been you might see if you search it, you will see that most of the accelerators are about 230 to 250 MeV in the case of proton, while in the case of carbon, let's say it is 12 times because energy per nucleon has to be same roughly. So the amount of energy which so it will be much costlier. So that is why they are not available right now. But the amount of energy or the heat generated there will be much larger. Is exactly I gave the very crude example last time that if a bicycle hits somebody or a car hits somebody, both are roughly having, let's say, even same velocity, but masses are so different. The damage done to the person to whom they are hitting will be much different. So it's exactly in a crude language one can understand that, but this can be translated to physics in terms of mathematics or in terms of momentum transfer, energy transfer, and all that. And then hence the energy generated, this energy deposited and the heat generated. So you can see that you can do that, but in a very crude language, one can understand that. In fact, people have found that some very trials have been done that they have done argon beam at one or two places. I think one place they have tried to treat the cancer with argon beam, and they found the efficiency of argon beam treatment is even much better than the carbon. So higher the mass, the peak becomes much sharper. At some stage it might become delta function. So that means if the cancer cells are confined to a very small region, then they will be killed within no time. But if the cancer is very big, let's say it is 5 centimeter or it is spread to 5 centimeter or 10 centimeter, then either you have to smear it or something you have to do it to kill all of them. So heavier ions are much better if cancer size is small because steering the beam, if it is proton, it is easier than the heavy ions.
Thank you, sir.
Okay, then next question, please.
So if suppose you are not able to answer ask the question here, and something comes later on, you don't feel free to put in the discussion group, and there I'll explain it, and I will upload the uh, answer on the piece of paper. So
Sir, sir, what are the possibilities to visit accelerators in Typer and Bach? Are there any possibilities?
see the more unfortunately. Uh, Now, of course, it is in a much bigger domain. For example, one proton cancer therapy system is there in Apollo Hospital in Chennai, and that is hospital. So you can, with the permission, of course, because there will be a lot of radiation and it could be harmful to you also. But you can visit perhaps with the, you can write to them, they will, most of the accelerators as of now were in DAE institutions, and there the entry is restricted. So there, I think, and now the visitors are not allowed in most of the places. At least in Bombay, BRC entry is completely prohibited. But I think with the permissions, it can be visited, but it's not very simple. But now there are many places where electron accelerators have been set up, and where they are open to the general public. General public means the vendors, because they take their materials there, get irradiated, and then so there it is easy. There relatively it is easier. See, there are always in the accelerator there are two sections. One is where you irradiate the sample, and other side is where the accelerator is. So that part is still restricted. But yes, should be possible. There are many places where it could be possible. Maybe not in large numbers, but if one or two people want to visit, it should be possible to do it. If you are really serious to visit an accelerator, then uh, I can request somebody. I am a retired papa, so I cannot do myself, but I can request somebody to for you to make a visit to the accelerators, which is outside BARC. But there is a big accelerator, DC accelerator in Tata Institute of Fundamental Research. They are more slightly less strict, more lenient. So I think it should be possible to visit that place.
Also, one can visit Peletron at TIFR. I don't think it's.
Other thing, Peloton is not only TF, that is the Tata Institute of one can visit. There is another thing where things will be slightly simpler. I won't say freely one can go. IUAC Delhi, because that is a center under UGC, and is made for universities. So I think IUAC people should be able to help without much problem. So if you want to see Peloton, and that is a roughly same or slightly bigger size, that is a 15 million volt terminal, and Tata Institute is 14 million volt, and I think IUC Delhi will be much simpler if somebody wants to visit. And here also some facilities which are used by the vendors around. There, I think it should be possible to visit this. Even exploratory, you don't say that you want to visit for doing the calculation. You say that you want to irradiate sample and you are exploring it. So you want to visit the facility. It should be possible. I mean, nothing is impossible.
IGCAR Kalpakam is also allowing students to visit, I think, sir.
Yeah, Kalpakam also it will be. The VEC Kolkata is security is not that tight because that's a completely research center. So you should be, and those people who are in the middle of the Indian, see for example, Bilaspur University, GG University, Guru Gobind Singh, not Guru, Guru Ghasi Ram University, Bilaspur. There they have a Peloton 3 million volt terminal. See, it's only whether it's 3 million volt or 14 million volt, the technology remains same. So I accept that length becomes easy and slightly it becomes difficult. But otherwise, there you can just walk in. It's a university. So those people who come from that area, they can just, I can tell there is a Professor Vajpayee. You can write to him and he will make arrangement. Or anybody who is in the Department of Applied Physics. They have unique tandem, this Peloton accelerator, and is for students. So anybody can join. So there are several east likely to come there. So that will be open for students. And then if you want to see cyclotron, then Punjab University Chandigarh is having a cyclotron. So one can go there and see all the components one can see. So there are many places. There is one in Amritsar or somewhere, some small IIT Kanpur is there. There you can just walk in. So I can, in fact, I suggest. I have written one article, Indian Accelerator Program in Overview, and I don't know whether you can see it. This is the book which has been published recently, and I have an article in that Indian Accelerator Program. So I have given history plus all the existing accelerators. Of course, very small accelerators I may not have included, but most of the accelerators I have included. This is, I think you can see it. This is a atomic energy in India achievements since independence. And there is an article by me and Dr. R.K. Bandari, who was director of VECC earlier. And it's a very good book. I think you should be able to, so you can have a look at it. This atomic energy in India achievements since independence. This book is so. In that article you can get reference to. I have given reference to each and every facility which I have mentioned in this, so you should be able to get it, and that will give the name of the person also to whom you should contact if they are still alive.
One thing I can add in here, in RRCAT actually there is a project placement cell. So project for projects they can apply, and for project they can wish that they want to do some project related to
Correct.
accelerators. Then there are 30 students each year we take for the projects. The student should be in the MTech or MSc, and project should be at least 6 months.
Okay, so it's a part of their curriculum.
Yeah, it is a part of their curriculum.
No, but what Amlendra, what he is talking about is visit.
No, such a visit is of individual is not possible. But if he wishes to do some projects related to accelerators, then
And
it is
spend-
possible.
And he spent few months.
And he spent few months, definitely.
But if you want to visit, I have told several places like Bilaspur you can visit. And hello, who asked this question? What is your area of from which region you come? Then I will tell you in that region which is the accelerator.
Right now, I'm staying in Kolkata. I'm studying in Tata Medical Center, MSc in Medical Physics.
Are Calcutta, though you have first is medical cyclotron, and then you have VEC, full VEC, several accelerators there. So Calcutta it should be very easy to for you to see visit.
So, actually, I have a visit at a park, and there's a Ampicon, All India Medical Physicists Conference. So I'm going to visit that. So if there is a
You can visit. Otherwise, if you are if you want to visit VEC center, then I can request Som, who is the director there, and he will make. If you instead of visiting alone, I think if team visits some few more students, because I remember in earlier there used to be students visits regularly, and I think VC they still allow it. So you catch a few more students and as a team 5-6 students or even
Sir.
faculty, but for and they will definitely allow you to come.
so we are group
Of
of
course,
16.
they don't have DC accelerator there; they have cyclotrons. But when the beam comes out, it doesn't matter whether it is coming from cyclotron or then beam is same.
We are a
VC
group of
is
6 members.
VC should be very easy.
Oh,
Okay, so anyone else want to ask something? Please go on.
So any question which comes to your mind later on, you can ask, you can send me this on discussion forum. You can send, so don't confine it to just this session. Anytime any question comes, but my request to all of you is that don't ask that kind of question, what is happening at 4 minutes to 40 seconds. And so that is not a question. You ask technical question. Because most of the questions were Rohit. Most of the questions were that, see what happened that in the beginning when we made videos, we made for 1 hour.
Mm-hmm.
Now then from NPTEL we were told that the video length should not be more than 20 minutes. So I said 20 minutes you cannot do it. So we made 20 to 30 minutes, and wheresoever topic is ending. So at that point we cut it and made in two parts. So some may be slightly 32 minutes, other maybe 28 minutes like this. So all lectures were broken into two parts. Now the lecture is one, topic is one. So people should see that or listen to that video, both A and B. Then the one topic is covered, one tight. Then you all that. See, many times it was happening. Some questions, if you see in that discussion, they will say that what is happening at time 26 minutes or something, and now at that moment the video is cut. So nothing is happening. Only you will see the advertisement of IIT Bombay and HBNI and things like that, their names and all. Nothing, because then if you want to see but we have taken care that that particular topic is completed at that time. Then only we cut it. We did not cut completely
Mm-hmm.
in between.
And
So
it's
when
labeled
you
part
see a
A,
B
part
part,
B. Yeah.
when you see a B part, then it will be a new subsection.
Mm-hmm. Yeah, this discussion we had last week also. Many people had this problem. They were seeing the B part first, and then they were having some
Exactly. Yeah,
confusion.
that's B part first and A part, or A part they are seeing only A part, and then
Mm-hmm.
they don't know what is happening later on. And suddenly they find at 25th minute we have stopped it, so they don't know why we have. So this is the reason for it. And the reason for what that is that at remote areas, I was told when I talked to NPTEL people, they told that the remote areas this internet speed is very low, so they are not able to download it.
Mm-hmm.
So there were a lot of complaints. So they said that if we have short videos, not more than 30 minutes.
Yeah.
In fact, they suggested 20 minutes. We requested that can we extend it to 30 minutes, because many of our lectures were not properly communicated if it is 20 minutes. So they agreed for that. And then, so you always see A and B together.
Yeah. Okay. Looks like there are no more questions. Uh, so yeah, as sir mentioned, you can ask your question later on the discussion forum also, and yeah.
No, if there is any particular question, then I will be as a coordinator. I will be joining.
Hmm.
Although the questions will be answered by respected persons. So next 4 weeks, I think Rajni Pandey will answer, and later on for 4 5 weeks, Amnendu Sharma will answer on the cyclic accelerators. But I will try to join every day, so that if there is any question, there's no boundary line. You can ask any question anytime. But since you are seeing the videos during that period, it will be. But otherwise, if any question comes anytime, you please flash on this discussion forum,
Yeah.
and we will definitely answer it.
Yeah.
And since this is last, officially last for 4 weeks are over. So I thank you, Rohit, for very nicely conducting the
It's okay, sir.
session.
So yeah, if there are no more question, I say thanks to you, sir, for joining and having a very nice discussion here. And yeah, thank you all for joining. And yeah, the video, everything is recorded here, so you can find this on the NPTEL website, the recording of this session also. And yeah, and see you next Saturday. uh, so yeah, bye.
Bye.